13.7. Let's just round one decimal place. We can only be as precise as our picture, so we don't have to be too critical about decimals here. Anyone have an issue with that? There's a difference between a negative key and a minus key on your calculator, so you got to make sure you're doing that right. That's why I'm asking you if you need help. This is the time. 3.7. What is, anytime we plug 0 into any exponential function, do y'all see what will always happen when we plug 0 in? It's always 1. It doesn't matter what the base is, right? Do y'all see that? Because no matter what this number is, raised to the 0 will give you 1. If that's a 2, if that's 0.27, if it's a 3, it doesn't matter. That to the 0 is 1. Okay, this is just going to be 0.27. This one, 0.27 squared. 0.027, or sorry, 0.0729. These are getting smaller. 0.27 cubed, 0.0196. All right, so I'm going to graph this now. I'm not going to write them as points. Does everyone agree that that's the input, this is the output, that's the input, that's the output? So I can... Now, unfortunately, I can't use this same graph, right? I could use the same x-axis, but I can't use the same y because look at our biggest y value here is 50. And yeah, I just can't, unfortunately. I'm going to have to put this on a different picture. So let me just erase this one. Keep that there. There we go. All right, so I'm going to go up. The biggest value I need is 50. So I'll count by tens. 10, 20, 30, 40. That's 10. Let's see how this goes. So at -3, I go up to 50.8. So -3, I go up to 50.8, and I'm just kind of eyeballing it there. Close enough. All right, not trying to land a man on the moon, just trying to draw a picture in a college algebra class. -2, get 13.7. So -2, here's 10, so I should probably just go up above 10, maybe about right there. Okay, at -1, we're 3.7, which is, I don't know, halfway would be 5, so somewhere around there. Of course, at 0, I get 1. 1's really, really far down here, right? Because that's 10, so 1's way down there. These are going to be really hard to draw, aren't they? 0.27, 0.07, 0.01. But we know the behavior, don't we? As we move from left to right, these are getting closer and closer and closer and closer and closer. We have a horizontal asymptote here, whereas on this side we have this thing taking off up to the left. And this is the graph of 0.27 to the x. All right, that's the graph of it. And this is known as exponential decay. Exponential decay. So what's happening here is that as you move from left to right, it's going away, right? So it's decaying away. The other example we had was growth. So that brings us to a conclusion, right? When it comes to exponential functions, if you're given some exponential function f of x equals a to the x, we have two scenarios. We will have growth In other words, our graph will look like this. If the A is bigger than 1. We will have decay. That means our graph will look like this. If the A is smaller than 1. Also, there's something else on this graph that they both would have in common. This point right here will always be 0, 1. This is what I was referring to a minute ago. We know that for any exponential function, if you plug in 0, you should get 1. So that should be a point on either graph, doesn't matter. For all exponential functions, all basic exponential functions, they should all go through the point 0, 1. So that's the y-intercept, in other words. Okay. That's the general idea of an exponential function. We good? So normally in a college algebra class, I have some flexibility on how much I want to talk about this and how in-depth I want to get to, like into this. But because of the things that are going on in the world today, I think it might be worth it for us to talk about exponential decay. Because I think all of us right now have to, I guess, entertain the idea that there could possibly be nuclear, weapons deployed at some point in time in the near future. It could happen, right? There's nobody here knows, right? What's going to happen in the next day, month, right? So what makes nuclear weapons so bad? Why are they so bad? I mean, they're very destructive, of course, right? Do you want to talk about this? I can move on. Do we want to talk about that? Kill a lot of people in one swoop, right? But relatively speaking, I mean, one very, very large nuclear weapon deployed in the middle of San Antonio, I think people outside 1604 would probably be okay, depending on how big it is. You wouldn't necessarily die in the initial blast, but what would happen after? So you have radiation, right? You have radiation. So that's the part that's, well, there's other shit too that's scary, but what happens is basically you get this material, this radioactive material. And I like to think of radioactive material like this, like a super microwave, right? Like you would never want to go stand in cram yourself into a microwave and turn it on, right? That just seems like that might be bad. It's kind of like what radiation is. Radiation is like a big microwave. And what it does is it messes up your DNA. So it goes in there and it changes your DNA. And so your cells in your body that used to say, oh, I'm going to do this, help you breathe. Oh, I'm going to do this and work as a muscle. Oh, they all don't know what to do anymore. And so your organs just kind of don't know what to do and your body just fails, right? That's radiation sickness. It's like you just got zapped by radioactive material, okay? So the problem with radioactive material, and this is whether or not there's a nuclear war or not, no matter what, we have all this nuclear material, all this radioactive material that we've made, humans have made, and we've got it in different places. And the problem with it is that it stays radioactive for a very long time. So I'd like to think about like a campfire. If you've ever gone out camping, you make a big bonfire, you're doing roasting marshmallows, right? You get too close to the fire, you're like, shit, that's hot, and you have to turn your face away because it's burning. Have you had that before? Okay. But you go out there the next morning, you go by the campfire, and it looks like it's out, right? But you poke it a little bit, and you see there's like red coals in there still. You wouldn't want to stick your fingers in there. Sorry about that. Forgot to mute that. It's still hot, right? Come back maybe 3 days later, then it's cool enough, it's fine, the fire's gone. Radioactive material is kind of the same way. It's very hot, and then that means very dangerous, okay? It's gonna zap the shit out of you, and then over time, it's less dangerous. The problem is that it follows an exponential decay model, and which means that, and this isn't a good one, this is more like it. It's like, okay, you start out, it's real bad, right? But over time, it's not so bad, okay? But see, it never goes away completely. See, it's always there. There's always some left. And the time it takes for it to go away is in the tens to hundreds of thousands of years. Okay, so it's not like you have some radioactive material that today is bad, but you know what, in 10 years it'll be fine. No. Like you'll all be, your kids' kids will not be able to go near it. You know what I'm saying? So it just never, there's no way to just put it out. So, we tried shoving it into mountains. We've tried doing all sorts of things. Some people think we should just send it off in spaceships and just launch it into the sun. The sun will just swallow it up and who cares, right? But it's very hard to do, right? And then what happens if you have a rocket full of bad radioactive material that crashes, that doesn't, something happens, it comes back down, it's a mess, right? So unfortunately, exponential models, decay models, model radioactive material, which is a very humbling thing when you look at the fact that we have a bunch of stuff that we can't get rid of. And if there's a nuclear fallout from a war, it's going to be there for a long time. So Chernobyl, you all know Chernobyl? You've heard of that, right? Yes? I see some people nodding. Y'all know what Chernobyl kind of is? There was a big old documentary on it. It was pretty popular, right? I didn't watch it, but there was fallout. Does anyone know how much material they lost control of in that nuclear reactor? Anyone know? Anyone take a guess?
Not a lot.
Not a lot? How much do you think? Take a guess. I'll give you a hint. It's less than the amount of weight I've lost this semester. I think it was about 12 pounds. I think it was about 12 pounds, 12 to 15 pounds. That's how much they lost control of. And that you can't even go to that place anymore. It's still contained, got all these, lead enclosures around it. I mean, that was back in the 80s. So just to give you an idea of what a small amount of bad stuff will do, and you just can't get rid of it. That's a very sad story. People went there that day and they covered it with concrete. Can you imagine this concrete truck pouring concrete on this hole in the ground, and everyone doing it knows they're dying in a few days, but someone has to do it, right? It's crazy. All right, I'm going off topic. That's enough with that. We will talk about half-life if I have chance. It won't be till after the test, though. So let's talk about what's going to be on the test, because that's probably the thing you're more concerned about, right? It's a little depressing to talk about half-lives of uranium. Hey. It's the world we live in. Okay, so on your review, do you think you can handle 7 and 8 now? Yeah? Do you understand what I'm asking you to do there? Just sketch it, right? So just make your little T table, draw me a picture, all right? And you don't have to be perfect. Just give me a general idea, okay? Make your table, use your calculator, draw your points, draw your curve, you're done. So that brings us to the next topic that's going to be on the test, and that is, where do we use exponential functions? Where are they used? They're used all over the place. But one place that I think you would find interest in is in banking and finance, and that's with what we call the simple interest formula. So before I can get to it, before I can actually get to that last idea on the review, I want to know if anybody has seen this number before. Y'all recognize that? What is that? Pi? Y'all heard of this number before? What is pi? It's just a number, right? It's approximately what? Does anyone know what that is approximately? 3.1415. Anyone know it any further now? 9, 2, who cares, right? Actually, a couple of days ago, they called it Pi Day. March 14th is called Pi Day because it's 314. I'm not a real big fan of that because it's actually, that's the number. It goes on, so whatever, Pi Day. All right, so y'all heard of that number? This is actually a very special number. We use it when we use circles, to find areas and perimeter or circumference and all that. This is a very special number. It's called an irrational number. And all that means is that these numbers go on forever and there's never a pattern to it. So think about a number like this, the number 1/3. 1/3, if you type that in your calculator, it's 0.333 and it goes forever. So this number goes forever, doesn't it? But there's a pattern, 3, 3, 3, 3, 3, 3, 3, okay? This is a number that goes forever where there is no pattern. So just keeps going, the numbers keep changing. We cannot predict the next one, okay? Any number that does that is called irrational. That's the one that most people have learned in their life. They've seen it, they know it's important, all right? There's another very important irrational number, another one that's very special, and it's the number e. Have y'all ever heard of that before? A lot of students haven't. It's just a number, just like pi, right? Why did they use pi? I mean, I don't know. They just used some Greek letter and said that's going to represent that number. Okay? Somebody chose it, all right? Pi, boom. E is another number that's very important that we assigned a letter to it. We said, hey, we're going to call this number E. And this number E is approximately 2.718, and it keeps going on forever. I should have said ... This keeps going on forever, and there is no pattern to it. All right? It is another example of an irrational number. This is a very important number when it comes to exponential functions. Because E, if you agree with me here, can be the base of a function. Because this number 2.78 is positive and it's not 1. So, like in theory, I could define a function f of x to be e raised to the x, which really just means 2.718 to the x approximately. Right? Now, gosh, excuse me. You might be asking why, well, you may not ask, I'll tell you. This is important, okay? For reasons that I can't explain in this class. Like, why is this such a special function? It wouldn't be until Calculus 1 that you actually investigate why this function is so important. So for us today, we're just going to have to accept that using e as the base of our exponential function creates this very special function. It's so special, in fact, we call it the natural exponential function. The natural exponential. In fact, historically, it was like mathematicians were looking for a function that behaved a certain way. We're like, I wonder if we could find a function that did this, this, this. And we went looking for it, and we said, hey, if we let the base be e, that's the function we're talking about. And we couldn't explain, we still can't explain why it is that this number does it, but it just kind of naturally does. It's like, why do trees have green leaves? I mean, you know what I'm saying? It's just naturally, that's the way it is. So this is the function that we were looking for. It behaves a very nice way in calculus, and so it's the natural exponential. So I'd like for us to think about what it would be if I asked you to graph this. Would it be any harder than anything we've done? No. You just make a t-table, x, e to the x, or f of x here, sorry. You go -3, -2, -1, 0, 1, 2, 3. And then over here you do e to the -3, e to the -2, e to the -1, so on and so forth, right? On your calculator, there is an e key. And so I'd like for you to take a moment to find it. I can't even find it on here. There it is. So for my calculator, for this calculator, I don't know about yours, I have a key on my calculator that has an L and an N. And above that key right here, it says e to the x. Does anyone have that on theirs? Yeah? So what I have to do, this is like a shift. This would be like a shift on a keyboard. I have to hit this other key first on my calculator. It says second. And what that does is, if I hit this first, then instead of being this function, it's going to be this one. So let's do e to the -3. the way I would type that into my calculator is this. I would hit the second key, then I would hit the LN key, and on my screen, after I do that, I get E, and it gives me a caret and a parenthesis. And now what do I want to plug in there? -3. Close the parenthesis and hit enter. And you should get 0.049. If you have your calculator, try it. Make sure that you can get this. And if you can't, let me know right now so I can help you figure out the keystrokes. Yes, you haven't? Let me see yours. Where the heck? May I?
Yes.
Okay. That is interesting. Let me get my glasses. This might help me. Okay, I found it. It's hiding from you on this one. Okay, so what I want you to do, see that PRB key? Hit that. Okay, now, oops, no, clear, sorry. Hit the second key, then that. Okay, and then what you want to do is move the arrow to the right. This sucks for you. And then do you see the E down there? Hit, there you go, hit enter. Now put -3. That kind of sucks, but that's what you're going to have to do. Yeah. I'll help you after class if you still need help with that. Second key, LN key, move to the right, option 2. Anyone else? You got it? I'm not going to do the rest of the table, okay? But you could then go graph this, right? Would this be exponential growth or decay? Growth, why? Because that number is bigger than 1. So it would be an example of growth. The bigger the number is, the faster it grows. So if this were 10 to the x, that would be, 10 to the x would be even faster growth than this one. How are we doing? All right. I want to talk about the finance thing, but I also want to talk about the 10. No, I'll wait on the 10. Well, let's get to the finance. So time for finally an application of this. So this is an application of exponential functions. There are many applications, all right? This is just one specific one. So this has to do with what's called simple interest. Simple interest. Simple interest. So we have to understand what interest is first, all right? So let's talk about finance just like very generally speaking. If this is a bank, right? If this is a bank, you've got people over here. Okay, you got people over here. These people have money. Okay, and then you got people over here that need money. Now, I'm not trying to say these people are broke or anything. I'm just saying that this person wants to buy a car. This person wants to buy a house, right? They don't have the cash, so what do? They go to the bank. They borrow money from the bank, right? These people, they have money in savings, right? Well, where do they put their money? They put it, bury it in the hole in the backyard. Some people do. Some people put it in the bank, right? So how does it work? The way the bank works is they take these people's money, right? If you have a savings account, a checking account, right, you have money in the bank, they take this money right here, and let's just say for an easy example, let's say you put in there $100, okay? You put $100 into the bank. The bank is going to say to you, okay, thank you very much for the $100. We'll keep it nice and safe here for you. And every month, we're going to pay you for letting us borrow your money, right? They're going to say, thank you for the $100. After a month, we're going to give you how much? How much do you think they give you for $100? Any idea? Probably like a penny. It'd probably be like a penny is all they would give you. Thank you. After a month, you now have $100.01. Thank you very much, okay? The bank does not give you much to borrow your money, all right? That amount that they give you extra for borrowing your money, that's called interest, okay? That's the interest. Now, what the bank then does is they've got all this money, right? They got all these people's money. All those people have put money in here. And what do? They say, oh, wait a minute. You want to go buy that TV, right? At Best Buy with your Best Buy credit card, right? And that TV, well, TV's not going to be $100, but let's use $100 just as to keep it equal to that. So remember, this person over here, they gained, right? They added to it 1 penny, right, after a month. Well, this person over here borrows that $100 from the bank, right? They borrow it. Thank you very much. And the bank says, that's fine, you can have the $100, but you need to pay it back. And we're going to charge you for borrowing that money. And do you think they charge you $100.01? No, how much do you think they charge you for that $100? On a credit card, what do you think the interest rate is on a credit card? 12 is low, I think, but yeah, 12 would be reasonable if you have good credit. 12%, maybe 16%, maybe 18%. 22%, I've seen it, 25%. So it's like, okay, great. You're gonna owe us back the 100, but you're gonna owe us back like 125, or let's just say 120. Okay? So you borrowed 100, but you're gonna wind up paying back 120. So how much did the bank make? They made 20 off of them. They had to give a penny back to this person, right? So they made like $19.99, whatever. That's how banks make money. They make money by lending out your money to somebody else.
You need to open a bank.
Yeah, well, the problem is that if all these people come for their money, right, say, hey, look, everyone go to their bank, right? They all go pull out money at the same time, the bank's gonna be like, oh, sorry, it's not here, right? They don't have the money sitting there in the bank. They just know that not everyone's coming at the same time. Right before the pandemic hit, right before the pandemic hit, a lot of people went to the bank and pulled out cash. A lot of people did. I know for my wife and I, we went and pulled out like 20% of what we had in savings, just pulled it out cash. Just in case, right? Just in case we couldn't get to the bank at some point, because everyone did that. It's like the toilet paper, right? When no one could find toilet paper, it's kind of like cash, same thing, right? Okay, so interest, this idea of interest is just a way of charging someone to either borrow money or charging someone or paying someone to borrow their money, right? So that's all it is. So there's a formula that we use to compute how much money you will either be paid to borrow your money or how much money you will owe if you borrow money from the bank, right? So here's the formula. Formula is A equals P times E to the RT. Now, I have to explain what all these letters are. I call this the shampoo formula because there is a shampoo called PERT Plus. I'm not going to be shy. I use PERT. It's close to my heart. It has E in it. E is the natural exponential. I can't go away from it, all right? PERT, right? So what does this formula represent? Well, first of all, P is going to be the amount you start with. So that would be, in this case, If you go put $100 in the bank, that's what P is. It actually stands for the word principal. Okay, the principal, that's the initial amount of money that you're either putting in the bank, or if you're the person borrowing, it's the amount of money you borrowed. Okay, so it's the amount that you start with. All right, R in the problem is what we call the interest rate. Okay, and it's usually given as a percentage. So on a credit card, you might have 12% interest, you might have 16%, 20%, but it's important that in the formula, when you're using it in the formula, this interest rate must be converted to a decimal. I'll give you one example under here, just in case you're not sure what I mean. If your interest rate was 12.5%, then in the formula, you would have to use 0.125 for R. So the way we convert percentages to decimals is we move the decimal point 2 places to the left. Right? So if you go in here, let's say you're working a problem, they tell you the interest rate is 12.5. If you replace that R with 12.5, it's over. You've made a mistake. You have to replace it with 0.125. All right? So that's what R is. T, I don't want to go down there, I'm going to go right here. T is time, and this is in years. You have to be careful with time, because the idea is this: if I put the money in there, right, I put $100 in here, then I'm going to leave it in there for a certain amount of time. So maybe I come back a year later and I take the money out. This formula is going to help me find out how much I would get back. If I left it in there for 2 years, then T would be 2. But if I left it in there for 6 months, that's half a year, I would replace T with 1/2 or 0.5. So you always have to make sure you're paying attention to the problem and how they're measuring T. With me? Last thing is what A is. A is the amount after time T. So let me show you how this works. I'm going to just give you an example. I always like to do the lottery example. Let's do a lottery example. Because this is always interesting. And maybe next class we'll talk about an example where you owe money. Okay, that's less exciting. So you win the lottery. You win lottery. Okay? How much do you want to win? Let's be realistic. Let's not say like $5 gazillion. Okay? What do you think? What would be a lottery that you would be happy to win? Let's just go $1 million. Okay. Now, if you won $1 million, would you be like, I'm set for life?